Welcome to a new video. Today we will talk about P&ID, piping and instrumentation drawing. So most of the time if you look at P&ID designation they will say it's a piping and instruments. But the reality is this drawing includes process, piping, instruments and control. On top of that we can sometimes include electrical and HVAC data in a P&ID. And in the electrical and HVAC data, maybe they are not for the process operator, but for the data recording only. So let's start our P&ID design by having some product in a tank, and we need to move this product to a distillation column. We need pumps. If we need to increase the temperature of this product, we need heat exchanger. Before you draw a tank, you have to think about what is the shape of this tank. It's a square, sphere, cylinder. Is it flat roof, fixed roof, no roof? It's above the ground, under the ground. Each one of these scenarios or these shapes may have a different shape. It's a cylinder with a flat roof, a cylinder with a conical roof, underground, horizontal, and a sphere. In our tank, we may show a vent. We call this a gooseneck vent. This means that your tank is atmospheric tank. This tank, it doesn't mean it's not atmospheric, but here we have a vent. We show here an overflow to a ditch or a drain. In this tank, we show something around the tank to protect the surrounding from the corrosive material inside the tank. We build a wall around the tank. Our process friends will go into a lot of exercise, a lot of things to be able to find the size of the tank. Bearing in mind that you have a capital cost, meaning building the tank itself will cost, and then you have a material inside the tank which costs money because the material in the tank is as if it is in the store. And then the tank will supply you with product for your production line and can, let's say, stay for 1 week, 2 weeks. You can rely on one tank. That's why you can find a refinery with many tanks. We call it tank farm because you need to maintain the production of the refinery for a specific time. And also the product from the tank, from the refinery has to go into a tank and so on. And then you can see the space available for your tank and so on. So our process engineer will give us the tank shape and the tank size in diameter and height. Now let's move into a pump. Bear with me, we will go back again and do everything in more details. For the pump, again, our process, they will define what type of pumps you need. Of course, there is a kind of experience here. So it doesn't mean that the process engineers who designed the system knows everything about pumps, but he knows that this kind of fluid is centrifuge. 99% of our pumps are centrifuge. Gear pumps and diaphragm, they are for specific needs only. But the process engineer will need to define the capacity of this pump, the head of the pump, and sometimes the power of the pump. There is many ways to show a pump on a P&ID. Here I show you about 3 shapes you can use. Now let's add the tank and the pump. It comes to the piping between your equipment. So now our piping friend comes in and help us. There is a valve attached to our tank, so we can isolate the tank completely to do maintenance, to do anything. And then there is a pipe to our pump. Here you can see different shapes of valves. So this is a manual valve. This is a motor operated valve. This is pneumatic valve. As a P&ID designer, you have to take care of equipment placement. The equipment placement will be followed by everyone. So you can see here you have isolation valve, So you can isolate your pump, suction, discharge valve. So if you close both of them, you can maintain, change, do all maintenance you need for this pump. This non-return valve, if you move it in this area, meaning moving this valve downstream of the check valve, you can also maintain the valve by closing the discharge valve and the suction. Let's now look at where you get all those lines and shapes and things. This is in the ISA. They designate a straight line for instrument or process connection. Dotted line or dash is for electrical signals. With strokes here, this is a pneumatic, hydraulic, and so on. So you can see now this line is a process line. You can see now in this drawing, we have two pumps, two redundant pumps, suction and discharge valves. So if you want to run this pump, you close, close, open, open. So pump A, assume this is A, will run, and you close, close, open, open, you run the second one. Because those are manual valves, the transition from pump A to pump B has to be done locally. If you want to be able to do it from the TCS, then what you need to do is move those valves, put a motor operated valve or pneumatic valve or something you can operate it remotely. So as we said before, you can see now this is very critical, the placement of the check valve. So I have to put it upstream of the isolation valve. So I'm not going to use this, I'm going to use this instead. All the four valves are manual valves, and they look like they are all the same size. We call them MV, manual valve. Another company will call them HV, hand valve. Do we need to give a tag for each one of them? Some companies, they do. They give one tag for each valve of these. Another approach is to give all the similar valves the same tag. The reason, they buy those valves in bulk. So they buy a gate valve, 4-inch, 50 numbers, and so on. So MV mean manual valve, 10 maybe mean a gate valve or a globe or a ball valve. 4 maybe the size, 4 inches, and so on. So we still in piping. Each one of those pipes has a designation number designated by the piping engineer during the design phase. The reason is each one of these will have its own isometric. ISO, we call it ISO drawing. The ISO drawing will include all the N-line devices, all connections, dimensions. So if you look at this pipe from here to this valve, all this valve pipe will have its own one drawing, shows all the lenses, number of elbows, number of T's, and so on, and also the size of them. You can see now they give each pipe a specific tag or a specific number. 04 maybe means it's a 4-inch. B maybe 300 pound. If it is A, it's 150 pounds line. W maybe water. The reason they give the W110 or the type of the fluid, when you select the pipe, you look at this thing and you go into a table, a specific table says for water, use this type of material. If it's seawater, use this type of material. Other thing is that when we do the design, we do it through modeling, 3D model. So the 3D model will give us at the end how many pipes you need, the lenses of all the pipes required for seawater, all the pipe required for gasoline, or required for sulfuric acid, and so on. So now you can have the material, all the material comes from the 3D model when you do this in the beginning. 4x6 mean we have 4 inch on one side 6" on the other side. If you look here, you can see this valve is a 6", meaning this line is 6". This valve is 4", so this line is 4". That means we have a transition from 6 to 4. So this is enlarger or reducer, 6/4 or 4/6. This is 2" line, which is the discharge of our pumps, 2" line, and so on. Let's go back to our process engineer and ask him to include more details. So the tank here, T122, the tank, and the process engineer will give us the dimension, diameter 10 meter, the height 5 meter, and sometimes they add a specific requirement for the tank. This is potable water, so it needs to be coated, or sulfuric acid, so need to do, let's say, a brake lining inside, so they will put it there. For the pumps, he said pump 122A/B, that means one of them is A, one of them is B. We did not define A and B because they are absolutely identical, but assuming from the first one you have a branch goes to somewhere, and from the other one no branch or branch to another place, that means we have to designate A and B to one of them. Here he said 200%, meaning they are 100% redundant. One of them is enough to run our process. We don't need to run both of them. Each one of them delivers 50 meter cube per hour at a head of 100 meter. In the tank, our process friend, he put HH, that means high alarm at 4.8 meter, high alarm at 4.5, and low alarm at 0.8, low alarm at 0.3. The difference between high and high, low and low is we approach the 4.5, we give the operator alarm at 4.5. If he could not manage the process and the level reach 4.8, we have to stop the process. We have to stop the feed because that will be overflow. When the level goes below 0.8 and then if it reaches 0.3, we have to stop the pumps. We have to trip the pumps, otherwise it will cavitate. So in the P&ID, we put the alarms and we put the alarms limit. As you can see the tank here, we have a transmitter, LIT, the equipment tank 1122, all the instrument attached to the tank. Its tag is driven from the equipment tag. So LIT means level indicating transmitter 122A. Why we have A? Because we have B. If we don't have another transmitter, I wouldn't put the A. Then it's connected by 420 milliamps or electrical signal to the DCS or the PLC for the HMI indication. Here the tag is LIT. The instrument engineer will buy a transmitter and the transmitter tag is LIT. The DCS engineer, when he receives the signal, he will show it on the graphic as LI122A. H, it means it's the high alarm. L, it means it has a low alarm. So the high and low is driven from the LI signal. The difference between this LI and this LI is the bottom one looks like it is a pressure-based device. The process operation needs to know the tank level, needs to know the alarms. Sometimes they need to know the quantity of liquid or fluid inside our tank. When we talk about tank level, do you want it in meter? If you have one tank 4 meter and another tank 10 meters, now you got confused. This is 2 meter and that 2 meters. So you will be confused if you have more than 5 tanks. So a lot of places what they do is percentage. So the level is in percentage. So this tank is 50% full, 20% full, and so on. So you have seen the alarm limits in meters. We have to convert it into percentage. The operator needs to control the feed and the level. What's the management want to see in a process? Sometimes we include some data in the P&ID for the sake of being transferred to the DCS for management only. Do need to show a maintenance stuff like the status of the transmitter, if it is failed or not failed. We show the transmitter failure by indicating the transmitter is failed by a triangle, small triangle, changing the color, the signal, so you know that the level which is you see from this transmitter is not valid. You have a problem with the transmitter. The maintenance engineer have their own DCS screens, their own graphics, and they show more data. Let's say a power supply status, network switch status, and so on. This is in the maintenance side, it's not on the P&ID. Where you get all those symbols? How you draw them? Do you going to invent them? No. Your starting point is ISA or ANSI symbols. So ISA gives you maybe 90 plus of all of the symbols you need in P&ID. However, sometimes you need to adapt it, to change it, to do some stuff to make it more suitable to your product or your lines or your devices or something. But I would say 95% of any process, you will find it in the ISA. Still, we are in our example, we have the tank, we have the pump, we have a suction, valve, manual valve, PI and PG. PG is a local pressure gauge. PI is a DCS indication value with a low alarm. In the discharge of the pump, you have the non-return PI, and I added another PI downstream of the valve. If this valve is closed, this PI will show the pressure of your pump, but this PI will not show the pressure of your pump. So placement of your devices, measuring devices, is important. Again, I have discharge gauge and flow indication. So this looks like it is flow based on an orifice flange orifice plate, and differential pressure transmitter goes to the DCS with a flow indication. You have the transmitter, dotted line, mean you have electric signals. In our case, could be a 4 to 20 milliamps. For critical process, we may use more than one transmitter to measure the same variable. In this tank, we have level indication transmitter LIT A and B, and both of them, they go into the DCS as A and B. So you can see in this example here, both of them LIs, they have two different indications, but the operator will run only from this LI 122, 1122. The high and low alarm is driven from only this bubble, not from this or that. How you select which one feeds or control this LI, that's under the operator control. So if this one always A, maybe, and then if something happens with A, it's automatically switched to B. Like if you have error comes from A, it's automatically, or it's from the operator, can switch between A and B. Here it's inside your DCS, so it's a soft link meaning it's a computer to a computer, it's a device to a device through communication link. All of them may be in the same controller or same CPU. You can see here we show on the P&ID the LIT. Here we don't show the LIT because we know any indication in the DCS has to be connected to a transmitter. So we don't need to show the transmitter. We know LI comes from LIT. In this case, we show the bubble and the DCS HMI or the PLC HMI only. What this will do, it will reduce the amount of devices on your P&ID, no more crowded P&ID. Now we will go into the ISA codes specification and look at how they show the symbols. So if you look at this drawing, they show us a circle and they said this is a field mounted device with a line. It's same but with an indication, with a square, that means it goes into the DCS, and here is in the field without this dash, so it means this is a panel mounted or indication. Here the ISA said that if you have a square and diamond, it's PLC. In a lot of places we use it for SI system. So again, as I said, you use this as your basis and then you change a little bit to better suit your process and your project. So now our process engineer developed the P&ID, but he needs some inputs. The inputs come from the piping. The piping engineer will tell him how to show the valves, which valve goes into which service, and so on. INC will give and review the instrument and put some his data. Mechanical engineer, HVAC. So the input comes from all those guys, so the process engineer can develop a good sound P&ID. Who reviews the P&ID? The process engineer has a pair, so some people from process department will review it, the piping department will review it, the INC department or discipline will review. If your P&ID is only for HVAC, you send it to the HVAC people to review it. Also the mechanical, if it is mechanical only P&ID, then you send it to the mechanical guys to review it. Who uses the P&ID? Everybody. As we said, civil engineers look at it, get some data, electrical engineer look at it and get some data, and everybody, of course, the INC and the mechanical guys, the piping guys, P&ID is the basis of their work. By this we conclude the video, and many thanks for viewing, and thanks for sharing and subscribe. And if you have any comment, please put it down, and see you in the next video.